Okay, so I think I've done it. I'll take my RFID sensor. I can see that I've got the green light there. And if I take my pineapple puck, which has the RFID tag at the bottom here, and I just stick these two close together, I want to look for that yellow light. And here we go. And
wow, so pretty.
Okay, that may have been a tad bit overly dramatic because RFID technology definitely doesn't have that kind of impact. With that said, RFID, or radio frequency identification, is changing the way we approach automation. Today, it is helping machines identify products and track them as they move through warehouses and factory floors. This ability to track products is generating real-time data that can be used to improve operations. RFID is also controlling access to equipment through badges and key cards. This increase in traceability is what's helping us solve problems that just a few years ago required far more manual effort. For this project, we're going to put that capability to work for us. Using RFID, we'll be able to identify which image is attached to this puck by reading the information stored on its tag. We'll also be able to write new information to the tag, allowing the puck to carry that information wherever it goes. So really, the goal is simple. We're going to present the puck to the reader and use the PLC to either retrieve information stored on the tag or write new information to it through our RFID system. So let's take a look at the hardware that's going to make all of this possible for us.
The first item on our list is the PLC. The PLC will serve as the brains of our operation, interpreting the raw information coming from the RFID tags and writing new information back to them when instructed to do so. Now, in automation, it's generally considered a good practice for PLCs to have their own dedicated power source. So for this reason, we'll be using a PLC power supply module designed to attach directly to the PLC CPU. Next, we'll need an I/O link master. For this particular setup, our PLC can't communicate directly with the RFID system. So the I/O link master will act as the middleman, packaging and unpackaging the raw data exchanged between the PLC and the RFID system. Now, some of you may be wondering, why are we using an RFID system that needs an I/O link master? Couldn't you have used a different RFID reader that plugs directly into the PLC? And the answer to that is, well, yeah, probably. But an I/O link master gives us a standard modular platform that allows us to expand the machine's capabilities without reinventing the communication architecture every time something is added to the system. And that's powerful because machines have a funny habit of evolving as the idea of what the machine should do is fleshed out over time. The machine today might only need RFID, but tomorrow it might need a smart button or an ultrasonic sensor, a pressure sensor, or something nobody planned for during its original design. With I/O Link, you can plug those devices straight in without adding extra communication hardware and simply configure your PLC to read the new data. Now, connected to the I/O Link master is our RFID antenna, which is responsible for reading information from the RFID tags and writing new information back to them. This is the component that actually interacts with the tags themselves. Now, I haven't quite mastered the interrogation stare that my wife has, so staring intensely at the PLC isn't going to intimidate it into revealing what it is thinking. So to give us a window into the process, we'll need a touchscreen display that allows us to see what's going on and interact with our system. We'll also need a way to program our PLC and touchscreen display. That means a computer running Windows to develop the PLC logic and touchscreen user interface that brings everything together. You'll also need a trained monkey for this step. Unfortunately, monkey training is beyond the scope of today's video. And finally, the PLC, touchscreen display, I/O link master, and computer all need to be able to communicate over Ethernet. To make that happen, we'll be using an unmanaged Ethernet switch. Now, if you'd like to build something similar yourself, Every component you'll see in today's project can be found through Automation Direct. With our components identified, let's move on to the wiring. Now, before we start throwing wires around like we're decorating a Christmas tree, let's talk some strategy. Because wiring a machine isn't just about making it work today. It's about making sure future you doesn't absolutely despise present you 6 months from now. Let's start with the PLC power supply. Our PLC power supply is designed to accept AC power directly. So we'll bring our incoming fused AC line into the power module to provide power to the CPU. And yes, this is the same electricity that burns your toast. So make sure you have a healthy respect for it, unless you're trying to recreate the opening scene of this video. Next up are the touch display and Ethernet switch. I think of these parts as infrastructure. Their jobs don't tend to change much over the life of the machine, and neither do their power requirements. Because of that, I like to keep them together on their own 24-volt power supply. Once they're up and running, chances are you won't have to think about them again for quite a while. Now, the IO-Link Master deserves a little extra thought. If there's one thing I've learned about machine design, it's that final revision is usually just another way of saying, see you next month. As more devices find their way onto the IO-Link Master, its power requirements can change right along with them. That's why I recommend looking at the IO-Link Master's maximum power requirements and selecting a power supply that exceeds that value. Don't just design for today's machine, leave room for the machine people haven't thought of yet. With power taken care of, we can connect our RFID reader to the IO-Link Master. One of the conveniences of IO-Link is that this single connection carries both data and power, which keeps wiring simple and makes adding devices much less painful. And finally, we'll connect our network together. That means the PLC, IO-Link Master, touch display, and our programming computer will all be connected to the unmanaged Ethernet switch. This gives each device a path to communicate with the others, allowing the PLC to exchange data with the IO-Link Master, the touch display to interact with the PLC, and our computer to configure and program the entire system. And just like that, the hardware side of our RFID project is complete, which means it's finally time to move to software, where we'll teach these boxes how to stop behaving like expensive paperweights. But before we do that, let's have a final build montage. Doggone it. I thought I finished this panel. Oh well, I guess it doesn't matter for this project anyway. Now, device configuration isn't exactly the part of automation that keeps people glued to their seats. And studies suggest that prolonged exposure to technobabble has been linked to boredom, confusion, and in extreme cases, brief self-induced comas. Fortunately, nobody's bothered to verify that. However, it might explain why movie directors usually cut away from the technical explanations as quickly as possible. Unfortunately for us, device configuration is a necessary part of getting everything up and running. So for the sake of your sanity, and quite possibly mine, we're going to keep this at a high level and focus on how all the pieces fit together. Now, if you're looking for a step-by-step walkthrough of the configuration process, Automation Direct has an excellent series of videos that covers every step, and I'll leave links to those in the description below. So the first thing we'll do is simplify our diagram by removing the components and wires we won't be talking about. You're still in the real system, we're just cleaning up the diagram so it's easier to focus on what matters. Next, we'll need to assign IP addresses to our PLC, touchscreen display, IO-Link Master, and programming computer. You can think of these like mailing addresses. If information is going to make it to its destination, every device needs its own unique address. Otherwise, it's kind of like trying to deliver mail to a neighborhood where every house claims to be 123 Main Street. If you're new to this, I recommend keeping the first 3 octets of the IP address the same, and changing only the last octet so each device has a unique address. Pair it with a subnet mask of 255.255.255.0, and you'll have a simple network that's easy to configure and troubleshoot. Now, if you're more experienced, you'll probably want to play around with the IP address and subnet mask to create the network structure you need for your system. The good news is, if you accidentally misconfigure an IP address, the world probably won't explode. The bad news is, you'll spend the next hour troubleshooting a network that insists everything is fine, even though it clearly isn't. And at that point, you'll probably wish it had exploded. Now, just because every device has an IP address doesn't mean they'll automatically communicate. First, we'll need to download and import device definition files for both the IO-Link master and RFID reader into the PLC. These files allow us to create the IO-Link tasks and device-specific data structures needed to work with our RFID device. In other words, this is the automation equivalent of introducing two of your friends to each other and hoping they get along. Of course, introducing people doesn't actually guarantee they'll talk to one another. To get the conversation started, we'll need to also import IO-Link master's EDS file and configure the Ethernet connections between the PLC and IO-Link master. Because right now, you're sitting on the same network with all the social skills of two engineers at a company picnic. When you boil this all down, configuration is really just 3 steps. Teach the devices where they live, who everybody is, and how to talk to one another. In automation terms, that's considered a healthy relationship. But communication is only half the battle. It's time to understand how RFID systems communicate with tags, what information is actually stored on them, and how we can retrieve and modify that information using our PLC. To really use RFID systems, we need to understand RFID tag memory and how the PLC instructs the reader to access that memory. The first thing we need to know is that RFID memory isn't one big storage area. It's divided into fixed blocks with a fixed number of bytes per block. Now, the tags we'll be using store just 4 bytes of memory per block. 4 blocks may not seem like much, but it's not like we're going to be binge watching Netflix on this thing. Instead, those blocks are much better suited for storing a part description, part number, part quantity, the current process step, or whatever information the application needs to associate with that particular product. Now, here's the important part. The RFID reader never decides anything. It simply does exactly what the PLC tells it to do, which, in our case, is probably for the best. The last thing we need is hardware going rogue. So what exactly does the PLC tell the RFID reader? Well, that boils down to just 4 instructions. First, where do we start? Second, how many memory blocks do we transfer? Third, are we reading or writing? And fourth, if we are writing, what data are we going to write? Let's walk through a few examples and see how these 4 instructions come together. Suppose a PLC tells the RFID reader to start at block 1 and read 1 memory block. The reader retrieves the data from block 1 and sends it back to the PLC. Now let's change the command. This time, the PLC tells the reader to start at block 2 and read 2 memory blocks instead of 1. The reader retrieves the data from blocks 2 and 3 and sends it back to the PLC. Writing works the same way. The PLC tells the reader to start at block 4 and write 1 block of memory. The reader writes the data to block 4 and reports that the operation completed successfully. Now let's write a little more data. This time, the PLC tells the reader to start at block 5 and write 2 memory blocks instead of 1. The reader writes the data to block 5 and 6, and then reports that the operation completed successfully. Of course, nothing in engineering comes without limits. Every RFID reader has a maximum amount of data it can transfer during a single operation. Since RFID readers always transfer complete memory blocks, the number of blocks you can access at one time depends on both the reader's byte transfer limit and the size of each memory block within the RFID tag. At its core, that's how RFID communication works. Now that we know exactly how the PLC controls the RFID reader, Let's go back and build the PLC program that makes all of this happen, and hopefully keep the magic smoke exactly where it belongs. Now, before we start doom scrolling through the ladder logic, I should mention that we won't be covering the touchscreen programming in this video. That's because the touchscreen programming could easily be a video all by itself, and we're focusing on the PLC logic that communicates with the RFID system. With that out of the way, there are a few variables worth pointing out because we'll be using them throughout the program. The good news is, we didn't have to define any of these variables ourselves. They were automatically generated when we imported the RFID reader's device definitions during the system configuration. First, we have our status variables. These tell us what the RFID reader is doing, whether a tag is present, and whether any errors have occurred. Next are the data variables. These contain the information being read from or written to the RFID tag. And finally, we have the control variables. These tell the RFID reader which memory blocks to access, whether to perform a read or write, and when to execute the command. Now that we know what these variables do, let's put them to work for us in our PLC program. Fortunately, this isn't one of those PLC programs where you spend 3 minutes scrolling just to find the bottom. There are only 13 rungs here, organized into 5 functional sections. The first section powers the RFID reader and monitors its status. There's no point in trying to read or write a tag if the antenna isn't ready. So the PLC first makes sure the reader is powered on and a tag is present. Until then, everything else simply waits. Next comes reading logic, which consists of rungs 3 through 5. The PLC waits for a read request from our touchscreen display, prepares a read command by specifying the starting memory block and number of blocks to transfer, and waits for the RFID reader to complete the operation. Once the data comes back, the PLC decodes the information so that it can be displayed on our touchscreen. This is the part where your application might do something completely different. But this is where the PLC turns raw RFID data into something useful. The write logic works much the same way. Rungs 6 through 11 wait for a write request, prepare the write command, and wait for the RFID reader to report that the write completed successfully. The remaining rungs convert the text entered on the touchscreen into a hexadecimal format that is then written to the RFID tag. Depending on what information you're storing, this conversion could look completely different in your application. Once either the read or write operation has been prepared, rung 12 tells the RFID reader to execute the command. And finally, rung 13 handles any errors that occur along the way, whether it's a communication problem or an unsuccessful read or write. The RFID reader reports that error back to the PLC so we can display it on the touchscreen and troubleshoot the problem. And that's all there is to it. The PLC waits for a tag, prepares a read or write command, executes it, processes the result, and keeps an eye out for anything that goes wrong. Now let's see this in action. Alright, so with the touch display up and running, and both the read and write functions ready to go, let's see the RFID system in action. Now, to make this a fair test, I had my wife secretly change the information on one of these RFID pucks before we started filming. That means I don't know which puck contains the wrong information, and I can't fake the results you're about to see. So, let's find the imposter. We'll start with the orange puck. Read the tag, and we get orange. So that one's correct. Next up is the pineapple puck. We'll read the tag, and pineapple. Looks good. Now let's check the starfruit puck. Read the tag, and tutti frutti. Well, that's definitely not right. Now, just to make sure that's the only problem, let's check the raspberry puck next. Read the tag, raspberry, perfect. So we found our culprit, now let's fix it. We'll switch over to the write function, enter star, well, apparently spelling star is harder than programming the PLC. And now we'll write that information to the tag. Now for the moment of truth. Let's read the tag one more time. And star. That's a success. And that's all there is to it. We use the PLC to read information from the RFID tag, identify incorrect data, write new information back to the tag, and verify that the change was successful. Now I hope you enjoyed this video as much as I enjoyed making it. If you found it helpful, please consider giving a like, leaving a comment, or subscribing to the channel. Until next time, this is Probably Grounded Automation, signing off.